All right, problem 3 is another application of scalar line integrals. This says to find the mass of a wire in the shape of the semicircle x squared plus y squared equals 1, and y is greater than or equal to 0, if its mass density at any point is proportional to its distance from the line y equals 1. So here is our wire, it's just the top half of the unit circle. And first off, to set this up in terms of a line integral, okay, well, if I know the mass density function, say, is delta, okay, then thinking about, say, a little differential arc length, ds, if I multiply my density function at a point times this little differential arc length, that's going to give me the mass of just this little piece of the wire. So then to find the total mass, I'm just going to sum these products up of density times arc length. Okay, so the mass here really is just the scalar line integral of our mass density function. So what is that mass density function? Well, again, in the problem it says its mass density at any point is proportional to its distance from the line y equals 1. So let's say I'm located right here at this point, and I'll go ahead and label the coordinates of this point xy. And now to find the mass density at xy, I want to know the distance from this point xy to this line y equals 1. So I want this perpendicular distance that goes from our point up to this line y equals 1. Well, this distance here would just be 1 minus y, right? Because the distance from our point to the x-axis is y, so this would just be 1 minus y. Okay, so then what is our density function? Well, delta then, since it's proportional to this distance, will equal k for some proportionality constant times this quantity, 1 minus y. All right. How about a parameterization for our path C? Well, just looking at top half of the unit circle, so I'll parameterize this as cos t sine t, letting t vary from 0 to pi. That's going to give us this counterclockwise parameterization. Okay, and so now let's go ahead and set up the integral. All right, so for the integrand, which is our density function, I want to evaluate that thing along our path. So I'm going to take k times the quantity 1 minus y and replace y with sine t. So that's going to give us k times the quantity 1 minus sine t. And notice our differential arc length, ds, that's just going to equal dt in this case because we're moving along a circle of radius 1, okay? If you look at the derivative vector, that's just minus sine t cosine t, and that has magnitude 1. All right, cool. And now we're left with this integral, and that's a pretty straightforward integral to compute. So you wind up getting that proportionality constant k times the quantity pi minus 2, which, by the way, is positive. You definitely would want to come out with a positive value. If it came out negative, that should make you pause. But yeah, no, we're all good here, and that'll do it for this problem. All right, thanks.